this. Sorry again. I have my computer just have this issue about overheating. Now I'm back in my basement again. I can't believe this. Every time I'm on the first floor, I have to go back to the basement floor. So this is now recording, and now I'm going to share my screen. And let's go back again to SPSS. And then we analyze, and we go to regression. We go linear. This is for simple linear regression, simple correlations, ANOVAs. And then we put our NCEE score as the dependent variable, and our predictive variable or our independent variable is the IQ, or what we call our constant. And then here in statistics again, that is the this is the default, but we're gonna need descriptives, and we're gonna add confidence interval to that. We don't need collinearity, we don't need part and partial correlations or R-squared changes, because we're not doing multivariate analysis yet. We're not doing multiple regression. This is simple regression. And we press continue. For the plots, we always want the Z of our predictive variable, and that is our X, and that our residual variable, which is the Z residual, as in our dependent variable, which is our, in this case, is the NCEE. And then we always want histograms, and we always want normal probability plot. This is our way of looking at the assumptions of the regression, which is homoscedasticity or homogeneity of the variance, and make sure that there is no heteroscedasticity in our data, to make sure that the assumption of regressions are met. We don't need to do save. We don't need to do all these fancy residuals of unstandardized or studentized or deleted. We don't need to do anything with this section of the, we just continue. And then we also, if we press this, we already got 0.05 of our F statistics, and that's a default. We don't need to change that as well. And we just press OK. And as I've mentioned earlier, this is going to be the output of your regression. So just in case the recording of that first video was not captured, I'm just going to quickly again review this, that the mean of our NC score is 30.27. We have an N of 88. The mean of our IQ score is 109. And the Pearson correlation is 0.221, which is a weak correlation, but still a positive correlation because there's no negative sign there. And it is statistically significant because what we have is 0.01 for the p-value for our one-tailed test. And then, but originally from our simple Pearson correlation, what we got was a 0.039. So this is a slightly lower p-value, but that is just a function by the time you use regression. It tends to have a lower p-value of the correlations. And right here, we don't need to look at the values entered or removed, because this is only for multiple regression. So that's blank. And then for the model summary, I've explained to you that the R is 0.221. That's the correlation, the Pearson's R, which is a weak positive correlation, and the R square is 0.049, which what that's our R square is always the shared variance between the independent and the dependent variable. And so basically what this tells us that only about 4.9% is accounted for by the IQ, on the shared variance of the IQ and the NCE score. The adjusted R squared is 3.8%, and this is very dependent on the size of your sample. We have 88, so that's why they are very closely related. 4.9, and we have an adjusted R square of 3.8%, accounting for the shared variance between the independent and the dependent variable. And our standard error of estimate is 3.78. And as I've mentioned, this is only, this standard error of the estimate is only correct based on the model assumption that the median score of our NCEA is 30.27. And the standard error of the estimate will not be the same if our NCEA score, median score, is not 30.27. So this is very parametric, and this is highly dependent based on the modeling of the regression. And we are using linear, because remember when we click here, analyze, and we say regression, I choose linear. So we are using a linear regression modeling, and that we are using the mean score of the NCE as our parameter, as our dependent variable. So if the mean score of NCE is 30.27. So that's how we interpret this section of the output of the regression. And then the ANOVA is just showing you 0.39, which is it's based on the F statistics table. So at the back of every big statistic book, you always have the T distribution, the Z distribution, the F distribution, and ANOVA uses the F distribution. And if you have a F statistic value of 4.404, your statistical significance is 0.039. And this is exactly what we get when we do a simple bivariate correlation between two variables, NCEE and our IQ. And we assume that it is parametric, so we use Pearson's, because Spearman is for non-parametric. And we press OK, and that's exactly what we're getting here. We're getting, for our Pearson correlation, is 0.39. So let's continue again with the most important part of regression are the coefficients, because this is what we're going to report on our final paper that we're going to submit to the journal. What the reviewer is going to be interested in is they want to know the coefficients in your regression, in your linear regression analysis. So what this tells you is that it's statistically significant. It uses the T statistics, is 2.099, and it's statistically significant because it's 0.039, which is less than the 0.05 significance value. And so we can say then that, that our IQ level is associated with, is positively associated, has a positive correlation with our dependent variable, which is the NCEE score. Now, as I mentioned earlier, that the constant, what that means is that conceptually, in regression modeling, the intercept, or what we call the constant, is the expected mean value of the NCEE when the independent variable, which is the IQ, is 0. So what this output means is that when our IQ is 0, the NCEE score, we expect the predictive value, we expect that based on our score, the dynamic relationship between IQ and NCEE is that when we have a 0 IQ, the NCEE score would be 14. And that is the beauty about regression modeling, is that it has a predictive power. So what about the unstandardized coefficient beta for the IQ score? What does this 0.148 means? What that tells you is that for every 0.14, or let's make this 0.15, for every 0.15 increase in our IQ score, it will also create a 1 point increase in our NCEE score. So that's what regression modeling is all about, and that is what this unstandardized coefficient beta is all about. So this is the beauty of regression, is that it has predictive modeling power, and that your unstandardized coefficient tells you the dynamic relationships of the variables, and at the same time, it tells you here that the greater the magnitude of the slope, the steeper the line, and the greater the rate of change. And that this maximum likelihood estimation will always try to estimate the various parameters such as your slopes and your intercept that best model to recreate the observed data. So when you look at here, that's what it's basically telling us, is that now with using the unstandardized coefficient, what it tells you then is that for every 0.15 increases in IQ score, it will create a 1 point improvement in the NCEE score using the mean parameter of a 30.27. So now we're gonna look at the next output. So this is the mean, and this is the most important output of regressions are the coefficients.
Okay, I have a question, Doc.
Okay.
You mentioned that the IQ score is statistically significant because of the 0.39.
Correct.
And how about the 0.72, Doc? When can we? What's the significance?
Yeah. Well, that has nothing to do. We are not interested in the significance of the constant, because the assumption of the constant is that the IQ is 0. We're not interested with that.
Yes, thank you.
Okay, we're only interested in this, in the beta coefficient right here, the standardized. That's why it gives you only one value here, the beta. Standardized coefficient beta is 0.221. It doesn't give you a beta standardized coefficient value here, beta, because we're not interested in that one, because that constant assumes that the IQ is 0. This is just part of the calculation of the coefficient. 0.9. Okay. So now the next one is to make sure that all the assumptions of our regressions are met. That's why we look at the residual statistics. What's the most important thing here is that the mean of the residuals are 0. So this here is 0.00. So that tells you that it meets the assumption of homoscedasticity or homogeneity of the variance. And going down is we still have to check the histogram, and that looks like the regression of the standardized residual is normally distributed. As you can see, it's a perfect bell shape. So that's another way to check that it is definitely meets the assumption that it's normally distributed, and that the variants are homogeneous. Just like in ANOVA, there's homogeneity of the variance, and that the null hypothesis in the Levine's test in ANOVA is that there is no difference in the observed variance. And so it has to be statistically significant in Levine. It cannot be statistically significant because in Levine's test, if you're able to reject that null hypothesis, then the variance is actually not homogeneous. So this is the equivalent of the Levine's test, is the standardized residual. And if you look at the PP plot is probability plot or percent to percent plot of all the standardized residual of your dependent variable. So this is one of the things that we told the SPSS to do, is the standard, the Z of the predictive independent variable, and the Z of, which is Z means standardized. And we plotted this, and this is what you want to see, is that all the observations are hugging the straight line, our linear model, and or straddling. There's so many words: straddling, hugging, higher affinity, but you know that the assumption is met if all of the observations fits in the line, okay? Because that's what regression modeling is all about. And then when we look at the scatter plot of the standardized predicted value, it looks like a bird's nest. It looks like it's scattered everywhere, and that is an indication of heteroscedasticity. And that is really important because that is an assumption of regression. And basically, what we can do here is that when you do a scatter plot, when we do a scatter plot of graphs, when we do scatter, X is our predictive IQ, dependent variable is Y-axis, and we press OK. So right here, this is our NCA score, and this is our IQ score. And if we fit a line, which is regression, this is where the slope is. You see, it's not very, the slope is not very steep, because that represents also that the association was only, the correlation was only 0.221. It was also quite weak. And that's why we're getting this. This is not, so basically the intercept where the Y and the X axis met is somewhere around 20, probably 28, because this is 25, 26, 27, roughly 28. So that is the intercept. And then another thing that we can do, which is this. This is our correlation, and this is our R squared, which is only, it tells you that it only accounts 4.9% of the shared variance of your independent variable, which is your x-axis, and your dependent variable, which is your y-axis, which is your NCEE. And that the variance that's being shared by your independent and your dependent variable is only 4.9%. It only accounts 4.9%. So there are still so many other things that we don't know that can predict the NCEE. Who knows the socioeconomic status? The richer the student, the higher the NCEE. Who knows another variable in the model when we do multiple regression modeling later on? Once we look at the different data, this is just simple linear regression where we plug in one independent variable. And who knows that if you are, let's see, what are all other, income could be a predictive variable that you could plug in. The richer the student, or the richer their parents are, or the income of their parents are, the higher is their NCEE score. So in this model, the independent variable IQ score only accounts 4.9%. It's a very weak correlation, but nonetheless, it's still statistically significant. It has a p-value of 0.039. So that's what linear regression is all about, and how is simple linear regression looks like in terms of ANOVA, in terms of Pearson R's correlation. So that's it. This is what regression is all about, is that we're able to, so what is the value of regression? It's this one. It's the unstandardized coefficient. Is that we're able to look at, using this model, we know that if our IQ is 0, our NCEE score will be 14, based on a model where the mean score of the